All right, hello and welcome. So today we'll be looking at stress in a bar due to what? Due to rotation. And above is the diagram of a bar of length L subjected to a y-axis. This rotating along y-axis and subjected to a centrifugal force. Of course, when anything is subjected to a centrifugal force, such things must what? Must rotate. Exactly. And it's going to have an angular velocity. All right. So now, at this point, here we are having from this point E to B is the mass, and from this point to this point is the section. The reason why we say, on a normal day this part is not there, but we need to section this part so that we can be able to calculate our stress and our what? Elongation. At least once we know the stress of this small section you are seeing here, then we can integrate to know from this point to this other point. So that is the reason why we are taking this part. And the length of this section is x. And from this point to this point is x. All right. And this point to this point is the radius. All right. Now you are going to take note of something. There's a tensile stress here. The tensile strength on EF is equivalent or is equals to the centrifugal force on what? On FB. So therefore, we can say that our centrifugal force, which is equals to mass times what? Mass times angular velocity. And we know that our angular velocity is equals to omega square r. And our omega is nothing but what? Angular what? Angular velocity. Why this one is what? Angular acceleration. So if I substitute this here, I'm going to have my centrifugal force to be equals to omega, m mass times omega square r. All right. So from here we know from the relationship of mass and what? Density. We know that density is equals to what? Mass over volume. So if we make mass the subject here, we can conclude that mass is equals to what? Is equals to density times volume. Density times volume. Right? And we know that our volume is nothing but what? Area times what? Times I. So we can therefore write our mass to be what? Density times area times what? I. So now, before I make my substitution here, let's consider the height for this mass in this place on this diagram. So that's what we want to consider now. So now, what is the height for the mass in this diagram? This is the part where we are having our mass, right? And from this point to this point is the height of the what? Of EB. All right, so let's get the height of the mass, that is length. So now we say that we take the length of this bar is from this point to this point is L. And once we section it, we are sectioning in the what? At the center, that is, and along the y-axis. So it means this section will divide the length into two equal parts. It means from this point to this point here, it's going to be what? It's going to be L over 2. And this point 2 is going to be what? L over 2. All right. So now, from this point to this point is L over 2. And from this point to this point is what? S. Definitely, if we subtract the full length, this half the full length here, from this S, we are going to get our mass here. That is the length for our mass. So, which is the height here. So, it means that our mass is going to be equals to density times area, then times what? Times height. That is L over 2 minus what? Minus x. I hope that is clear. So that is the height. All right. Now the next thing we want to consider here is let's go for our radius. Now let's go for our radius. All right. You need to listen carefully. Now for the radius now, we said that the length of this part is nothing but what? It's nothing but L over 2 minus S, right? L over 2 minus S. All right. If I decide to divide this point into two equal parts, it means that means that this point, from this point to this point, is going to be half of this, half of L over 2 minus S. So it means that this point is going to be half into L over 2 minus S. And this other point too is going to be half into L over 2 minus S. All right. Now, and you know, from this point to this point is our what? Our R. And don't forget, this is our S. From this point to this point is our S. And we know from this point to this point to be what? Half into L over 2 minus what? S. So it means the summation of S plus half of L over 2 minus S is going to give us the what? The length of this what? Of this radius. Because our R here is radius. So it shows that I said S plus half into L over 2 minus S. I hope this is clear. All right. All right. So now the next thing we are going to do is we are going to make our substitution now into this equation now. So here we are having our mass to be density times area times, so we are going to say centripetal force, centrifugal force is equals to density times area then into L over 2 minus S. Multiply by R. R is what? S plus half into L over 2 minus S. All right, so here I omit omega square. I omit omega square. So let me just clean. Let's rewrite this because I don't want you to miss out on this. All right, then our Buga force is equals to mass. Our mass is density acceleration into L over 2 minus S multiplied by omega square. So we are going to have omega square, then multiply by our radius. Our radius is S plus half into L over 2 minus. All right, so from here, I can say that our F is going to be equals to density area omega square into L over 2 minus S multiplied by, let me just open a big bracket here, S plus half times this is going to give us L over 4 minus X all over what? X all over 2. All right. So from here, if I continue with that, I'm going to have F to be equals to density times area omega square into L over 2 minus S into X times minus S minus X over 2 is nothing but what? X over 2. So we are going to have L over 4 plus X all over 2. All right. So from here, I can factor out 1 over 2. If I factor out 1 over 2 from here, I'm going to have F equals to density area omega square into L all over 2 minus S. Then if I factor out 1 over 2, I'll be left with L all over 2 plus what? Plus S. All right. So I can decide to move the 1 over 2 to this other side. So I'm going to have F to be equals to 1 over 2, then density A omega square into L over 2 minus S into L over 2 plus what? Plus S. You can see this is looking like what? Difference of 2 square. So for me to expand that bracket, I will not waste my time there. I know the idea of difference of 2 square. So I have A omega square into, so from the idea of this 2 square, I'll just multiply this with this. I'm going to have L square over 4 minus S square. All right. So this is the centripetal force. So this is the, we can conclude that this equation here is the centrifugal force of this bar. All right. So now the next thing we want to consider here, our stress. We want to consider stress. We know that stress is equals to what? Force all over what? All over area, right? All right. So now, by the time I substitute this centrifugal force here, I'm going to have my stress to be equals to half into what? Into density A omega square into L square all over 4 minus S square all over what? All over A. So this A, we cancel out this A, then our stress will be equals to 1 over 2, then density omega square into L square all over 4 minus S square. So for the proper way of writing this, you can say that stress is equals to square into L square all over 4 minus S square all over 1, all over 2. All right, so this is the stress. This is the stress. All right, but we are going to have maximum stress at which part? At the part where our S is going to be equals to what? 0. So maximum stress, we are going to have maximum stress at S is equals to what? 0. So at S is equals to 0 here, our maximum stress will be equals to density omega square into L square all over 4 minus 0 square all over what? All over 2. So by the time you do this, our maximum stress will be equals to this L square all over 8. So this will be our maximum stress. All right, so the next thing we are going to consider here is we are going to consider our what? We are going to consider our strain. We are going to consider we are going to consider strain. All right, so we know that our Young modulus, which is denoted by E, is equals to stress all over what? All over strain, right? So make strain the subject. I'm going to have strain to be equals to stress all over what? All over what? All over E. All right, so we are going to substitute our stress here. I will have here, so it means strain is going to be equals to what? It's going to be equals to density omega square into L square all over 4 minus S square all over 2 divided by E, which is going to be what? 2E. So we are going to have this to be 2. So this is our strain. All right, now we are also going to consider strain again because we know that is, know that strain is also that is the change in what? Deformation, that is the change in length, that is change in length all over what? The original length. But the original length we are considering here is the original length of what? Is the original length of this string, that is of this diagram you are seeing, and the original length here is nothing but what? Is nothing but the S. So we are going to say L is equals to ds. So it means this is going to be all over what? All over ds. So now we are going to equate this equation and these equations together now. So by equating the two equations together, I'm going to clean up this part. By the time we equate, we are going to have our deformation, this elongation all over the S equals to density angular velocity square into L square all over 4 minus L square all over 2e all over 2. All right. So by the time I cross multiply, I want to make the deformation the subject of formula here. That is the elongation dl to be equals to density omega square into L square all over 4 minus L square all over what? 2e then yes. All right. So now this is just the deformation of this small body now. This is just the deformation of this. Everything we have done is we consider what we have here. Now, for us to get the full body now, we can do two things. It's either we integrate from this part to this part. It is half, since this section divided into two equal parts. When we integrate from this part to this part, anything we get we multiply by 2 and we get the full length. I think that one will make our work easier. Or you can integrate from this part to this part, that is from 0 to L directly. You arrive at the same answer. All right. So for us to integrate, we are going to integrate the brackets keeping this constant. So we are going to say the head will be equals to all over what? All over 2e. Then we are integrating from 0 to half. We are integrating from 0 to half into what? Into s square all over 4 minus s square all over, that is into what? Into dx. All right. So now, for us to do this we are going to say the L will be equals to what? Will be equals to density omega square all over what? All over 2e into, by the time we integrate this, we are going to have L square all over 4s minus x to the power of 3 all over 3. Then we are moving from 0 to 1 all over 2. All right. So now the next thing we are going to do is for us to get the total elongation now, because we just consider half of this section from this point to this point, that is from 0 to what? L over 2. Now for us to do the full now, we are just going to multiply by what? By 2, because the section is divided into two what? Into two equal parts. Exactly. All right. So now by the time I multiply this by 2, if I multiply this by 2, these 2 here will go with these 2. Then I'm going to have my deformation, as density omega square all over e. Then into, we make our substitution for the upper part alone. The lower part is useless, 0. Because if we substitute 0, we'll get 0. All right, so we are going to substitute L over 2. Sorry, this is not 1 over 2. This is L over 2. All right, L over, oh, sorry, L over 2. L over 2. All right, because we move from 0 to L over 2. All right, so by the time we substitute L over 2 for S here, so we are going to have L times L square, which is going to give us what? L cubed. All over 2 times 4, that is 8. Minus, if we substitute L over 2 here, we are going to have L cubed here as well. So we are going to have L cubed all over 2 times 3. 2 times 3 is what? Is 6. All right, so we close the bracket. So the next thing we are going to do is we are going to clean up this part. All right, so sorry, by the time you substitute L over 2 in this S here, I'm going to have L cubed all over 2 to the power of 3. 2 to the power of 3 is 8, and 8 multiplied by 3 is 24. All right, so now here we can therefore say if we continue with that, we are going to have our deformation to be equals to this into omega square all over 1, all over e, all over e, all over e into if you want to go for your LCM method, you want to have 24 here. 8 in 24 is 3. 3 times this, we are going to have 3L cubed minus 24 in 24 is 1. 1 times L cubed is what? L cubed. So by the time you do this, we're going to have our total deformation equals to this omega squared all over into this 2L cubed all over what? 24. And you agree with me that 2 will go into 1. 2 here is going to be what? It's going to be squared. All right, so now I'm going to say the L here is going to be equals to this omega square all over, that is L cube, all over what? All over 12. So this is going to be the total and the total deformation or elongation. This is going to be the total elongation or deformation of the bar. All right. So I believe you have learned something new in this video, this content. So please don't forget to give us a thumbs up, and don't forget to also drop a comment. You can tell us how, let us know how we have been teaching so far. Are we simplifying it enough for you, or you are finding some parts to difficult to understand? You can let us know. We are always free to attend to you. And don't also forget to join our WhatsApp group. The link is in the description. Don't forget to subscribe to our YouTube channel and turn up your notification bell. But anytime we upload a new video like this, you are going to receive them.